So we're looking at two different special types of functions today. The first is called composite functions, which we get from doing what we call function composition, which means just putting two different functions together. So you're plugging one function into another function. So you should have done a little bit this in Algebra 1. You probably just saw this notation though. So f of g of x or g of f of x, so one function inside another function. There's another notation here, it just means the exact same thing. So that little circle in there we read as of f of g, and then this is of x here. It's important you understand that this is not times x. This isn't multiplication here, just like this is f of x. It's not f times x, of course. So if we look at this one right here, it can be helpful first to rewrite it with the notation that you're used to. So this is f of g of 3. So everything goes in the same order in both notations here. And so this 3 is your x value. The 3 is the x right here. And so what we do is first we plug the x into g of x. So we're going to kind of work this one backwards, kind of from the inside out here. So first we're going to ignore everything else and just find g of 3. Pretend that the whole problem is g of 3, right? And so what you're going to want then is you're going to want to take 3. 3 is the x, plug it in for x right there. So you'll have 3 squared plus 1. The thing is, though, whatever we get from this, we're going to have to plug into f. The problem isn't just g of 3, it's f of g of 3. So we have to have f of 3 squared plus 1. Well, of course, 3 squared plus 1, 9 plus 1, that's 10. So if it was just g of 3, if it was just 3 squared plus 1, we'd have 10. But then we still have to find f of that answer. So we're taking x and first plugging it into g, and then the answer we get is what we plug into f. Well, f of 10, of course, would be 2 times 10 minus 3. 20 minus 3, we get 17. All right, so what about this one here where we don't have a particular number? So you can still start by rewriting it the way that you probably saw it in Algebra 1, which, by the way, you would have seen in Algebra 2 as well if it weren't for the pandemic in the spring. And so, well, let's just go ahead and replace f of x with what we know f of x is. Again, we're going to kind of work these inside out. So we don't have a value for x, so we don't have anything particular to plug into f. So let's just write out what f of x is. So this is g of 2x minus 3. I can replace f of x with 2x minus 3 because they're the same thing. Okay. So then what this means is take 2x minus 3 and plug it in wherever we see x. Wherever we see x, we replace it with 2x minus 3. So I'm going to have 2x minus 3 squared plus 1. And then, of course, 2x minus 3 squared, make sure you don't just try to distribute a squared. That's not a thing. You can't do that. I got to actually multiply that all out. 2x minus 3 times 2x minus 3, multiply that all out. And you'll get 4x squared. And then you'll get minus 6x again. It's minus 12x. And then plus 9. And then there's something that people frequently forget in this kind of thing. Do you see what it is? It's that plus 1 at the end often kind of gets dropped. Don't forget that little thing at the end right there, plus 1. And so then our answer here is 4x squared minus 12x plus 10. Now you might look at that and wonder, I wonder if that's factorable. I wonder if I should try to factor it. There's something in the directions that tells you whether you should or whether you shouldn't. It's this right here. It says find and simplify. The fact that it says simplify means that you should not factor. Simplifying and factoring are opposites. I always laugh in the Algebra 1 class. What happens sometimes is the kids will kind of go back and forth. So we'll give them something and says maybe factor, I don't know, x squared minus 2x minus 3, and so then they'll look at that and go x minus 3 and x plus 1, and then they'll look at that and they'll say, oh, I know how to multiply that all out. And so they'll multiply it all out. I'll have the x squared and plus x minus 3x and then minus 3, and then they'll combine their like terms, x squared minus 2x minus 3, and they'll circle their answer, and they'll be so proud of themselves. They did so much work, so much algebra. Think that they're all good, not even realizing that they got back to where they started. So if you factor and you simplify, or simplify and factor, you're going to undo everything that you just did. So make sure that you know the difference between simplifying. So this direction right here would be simplifying, where the answer looks like this, versus factoring, where we stop right here. All right, they're opposite processes. They would undo each other. So if I say simplify, I don't want you to factor. Just go ahead and stop right there. Okay. All right, well, why don't you guys go ahead and try problems 3 and 4 here, using the same functions, find these two things right here. And you can go ahead and double check your answers right there. On this one, we had x is -1, so we plugged in -1 into f of x. F of -1 is -5, and then we take that answer, -5, plug it into g of x. And then here we wanted f of g of x, so we take g of x, we take x squared plus 1, and we replace x with x squared plus 1. All right, so that's it for function composition, for composite functions. So now we're going to take a look at something called inverse functions. So let's say we have a function where we input the x, output the y. We've got a nice rule for that. What if we want to go backwards? What if we want a rule where we input what used to be the y values, and it will output what used to be the x values? So, maybe we had something else in our table right here. So it was something like, I'll make it an easy one that you could probably see. And say we had 21 right here, and we wanted to figure out what was the x that got us the 21. Well, if we had this, what we're going to call an inverse function, then we could just use that rule. We could say, let's plug in 21 into whatever this rule is right here, and it will tell us what the x would have been. It'll be a y over here, it was an x over here. The x and y are going to swap because the input and the output swap. Okay, so what that's going to mean is that since the x and y swap, that the domain and range are also going to swap, because domain is just the possible x's, range is just the possible y's. So whatever the domain is for f of x is going to be the range for the inverse. Whatever the range is for f of x is going to be the domain for the inverse. And so this is the notation we use here, this f to the -1 here. It's not actually f to the -1, though. It's not like we're taking this function and raising it to the -1 power. This is just the notation that we use. The -1 is just inverse. It has nothing to do at all with an exponent of -1. It's actually kind of a strange notation that we even use that. Right? There's a reason it has to do with multiplicative inverses. Reciprocals are the same thing. But anyway, okay, so let's take a look at if we want to find the inverse. To find the inverse, we're just going to use that idea of swapping x and y. So first, what we want to do is we want to go ahead and just swap f of x with y. Of course, f of x and y are the same thing. So now that we've got x and y in the picture, we can go ahead and swap them. That's what the inverse does, swaps the input and output. So we'll make yx, and we'll make xy. And then, well, if we're going to have a function, if we're going to have a rule, then we want it to be in y equals form. That's going to be what's useful for us. So now let's solve for this y right here. So I'll subtract the 1 over. X minus 1 is 2y. And then I'll divide by 2. And I'll get that x minus 1 over 2 equals y. And that's going to be my inverse function right here. So this y is now f inverse. I can say the f inverse rule is x minus 1 over 2. And so now I can answer this question here. If I want to know what x do I start with to end up with 21 in the function, well, in my inverse, I can start with 21. I can plug in 21, figure out, all right, 21 minus 1 is 20. 20 divided by 2 is 10. So over here, I plug in 21, I input 21, and I output 10. And that tells me over here that the input that I would need to get 21 was 10, which of course that was an easy one. We could have just looked at that probably and figured it out. But this is a nice rule where if it was something more complicated like 573, then I can use the rule right there. Okay, so it's a rule that allows us to go backwards to figure out what was the x for the y to switch the input and the output. Okay, let's see what that looks like graphically. Let's graph these two functions and see what does it look like to swap the x and the y. All right, so my original function was 2x plus 1. And then, so to get a fraction that looks like a fraction, I'm not sure if we talked about this yet, but you can hit alpha y equals. If you hit alpha y equals, you can type a fraction that looks like a fraction. And I'll put x minus 1 over 2. If your calculator doesn't do that, just make sure you put parentheses around x minus 1. And then I don't just hit graph, I hit zoom 6, zoom standard. And there's our two lines right there. So you can see there's this kind of some symmetry here. There's a line that if I graph this line right down the middle, a line that splits them right down the middle, they would be symmetrical about that. If you might try to guess what line that is, see if you have any clue what it might be. It's actually just y equals x. If you graph y equals x, it's going to split those right down the middle. So actually finding the inverse, swapping the x and y, is actually just reflecting, flipping across the line y equals x. The function and the inverse are going to be symmetrical about y equals x. Okay. Now the formal definition, if you really wanted to 100% verify or prove that things are inverses, you actually use function composition, what we just did at the beginning of this lesson. You plug them into each other. So I'll find f of f inverse first. And so that means I want f of this x minus 1 over 2. So I'm going to take x minus 1 over 2 and plug it into f of x in the function, replace x with x minus 1 over 2. So 2 times x minus 1 over 2, and then plus 1. So you can see what happens here, why this is going to work. The times 2 and the divided by 2 cancel each other out. And then the minus 1 and the plus 1 cancel each other out. And so we get to just x, which is what needs to happen for them to be inverses. It's kind of like squaring and square rooting. Squaring and square rooting cancel each other out. If you take 5 and you square it and then you square root it, you get back to where you started. That's the idea of function and its inverse. Inverse is kind of like opposite. Okay, so that's one part of verifying. We also have to go the other direction. There actually are some functions where if you plug them into each other one way, you get x, but the other way doesn't work. So I'll do the other way here. Now we'll take f of x and we'll plug it in here. So we're going to find f inverse of 2x plus 1. So in my inverse function, I'm going to replace x with 2x plus 1. So I'll have 2x plus 1 minus 1 over 2, which is, again, the same thing's going to happen. The plus 1 and minus 1 cancel, just in the reverse order now. And then the times 2 and divided by 2 cancel, and I get x. And it does always have to be x. It's not just that these are the same thing. It's that I have to get x. So that's the formal definition, verifying that they're inverses, plugging them into each other, making sure you get x. Now, here's something though, not actually all functions have inverse functions. Take a look at just our good old y equals x squared, a simple parabola. Okay, so of course a parabola is a function. The fact that we've got different y's, or sorry, the same y for different x's, not a problem. We're talking about even if every point had the same y. That wouldn't, even if it was a horizontal line, a constant function, that is still a function. But take a look at what that would mean for the inverse. So the inverse swaps the x and the y, and now see what happens. Now we've got the same x with multiple y's. Now the inverse is going to fail the vertical line test. Okay. Well, let's try to figure out a test that we could have used to figure that out. Let's see if we didn't know this right here, how could I look, and let's say, we don't want to just have a table of values. Let's just say that we had this. How could we figure out whether or not the inverse is a function? Okay. Well, if the inverse is going to fail a vertical line test, switch x and y, and that means that the original function is going to fail a horizontal line test. So we use a vertical line test to see if something's a function. We use a horizontal line test to see if the inverse is a function. So let me show you some different examples of this. So these are all different types of, a relation is the most general term. So not everything is a function, but everything is a relation. All kinds of graphs, all kinds of equations, they're all called relations, and then functions are a special type. Okay. So if we take a look at this one here, it is a function because it passes the vertical line test. But the inverse would not be a function. If we reflected across y equals x, if we swapped x and y, then the inverse would fail the vertical line test. It's because this one fails the horizontal line test. Right? So see if you're a function, use the vertical line test. To see if your inverse is a function, you use the horizontal line test. And again, the test is if I draw any vertical line, could it ever pass through 2 points? If I draw any horizontal line, could it ever pass through 2 points or more? Okay. So this one is not a function because it fails the vertical line test. We've got a single input with multiple outputs. But the inverse, if I swap x and y, if I reflect it across y equals x, the inverse now would be a function because this right here passes the horizontal line test. Every horizontal line, if I draw every horizontal line, it's always going to pass through only 1 point. Okay? All right, now this is what we're going to call a one-to-one function. It is a function, passes the vertical line test, and its inverse is also a function. This passes the horizontal line test. All right, we call this a one-to-one function. That's what you have to be to both be a function and have your inverse be a function. You have to have exactly one x for each y, one y for each x. There's no repeats going on here. All right, one-to-one function. All right, so why don't you guys go ahead and give these problems a try. So you want to see, does the function have an inverse function? And you can go ahead and use your calculator for this. We're looking at the graphs. So you can just go, if you think you have a good idea already without your calculator, then that's fine. But you're welcome to use your calculator to think about what these graphs look like. Think about, would they pass the line test that we would need to have an inverse function? And if it has an inverse function, if it passes the horizontal line test, go ahead and find it. If it doesn't, then you're done. All right, go ahead and give these two problems a try. So here are the answers for those two problems. So the first one was yes, cubic function is one-to-one. So this is a function and its inverse is a function. It passes both the vertical line test and the horizontal line test. And so we could find the inverse. And so when I cube root both sides, I'm able to find this inverse. Notice that when you cube root both sides, that you don't have the plus or minus, and so you are fine. Odd roots, you're not going to have a plus or minus. If we tried to solve for the inverse up here for our parabola for f of x is x squared, then we would have had to end up square rooting both sides, and so we would have gotten a plus or minus. That would have been another way to tell the inverse was not a function because of that plus or minus right there. But the odd root right here, we don't need a plus or minus. And then for the second problem, you didn't have much to do. You look at the graph, it fails the horizontal line test. You can draw a horizontal line that passes through multiple points. So the inverse is not a function, so you can just stop and you're done.